Hello guys, this is review for physics. So we're going to cover Newton's laws and forces. So first law, an object in motion stays in motion and an object at rest stays at rest unless acted on by an external force. So an external force just means a push or a pull. Alright, so a force is just a push or a pull. And when you say that an object is at rest, well, that object ain't moving. But if an object is in motion, then it is moving. Now, if you got a person that's at rest, and let's just say that this person is sleeping. He has fallen asleep and he is not moving and he is at rest. If you do not push or if you do not apply a pulling force to the person, he's still going to be at rest. So if I do not apply a force to something, an object at rest, it's not going to move at all, right? And so that is the first part. If you have an object that is just at rest and you don't do anything to that object, it's still going to be at rest. And likewise, let's say if I got a car, all right, and let's say it's moving this way at a constant velocity. So there's a constant velocity to the car, which I'll just call it V. All right. Now, unless I pull on the brakes, well, this car is just going to continue moving forward at the same speed or velocity. Now, one question you might be having is, well, that's not the case. If I roll a ball on, let's say, a mat, well, the ball is I roll the ball and it's going to stop at some point. It's not going to move anymore. Why is that? And the reason why when you roll objects and they stop, that's because of something known as friction. Friction is a force and it basically resists an object's motion. So when you have an object that's moving, chances are that you got friction going on, all right, which is basically in the opposite direction of motion. So the force of friction would be in the opposite direction of which the object is moving, and it resists this motion. So therefore, this object would soon get to a point where it's just not going to move at all because of the force of friction. It's going to be taken over, right? And then soon this velocity term, that's going to die out, right? So the object is just going to get slower and slower. It's going to decelerate, and then it's going to just come to a stop. And another factor that you have to take into account is something called air resistance. So basically, it's exactly what it sounds like. The air is sort of blocking this ball. Think about all those particles in the air that is basically just blocking the ball from going forward. So these are just two factors that you have to take into account in real world scenarios. All right, when you're dealing with objects rolling in real world scenarios, chances are that if you roll an object, it's probably not going to stay in motion for long. But in an ideal world, what Isaac Newton's basically saying is, in an ideal world where there's no friction at all and where all surfaces are perfectly flat, no friction at all, no air resistance, well, in that case, the object would just keep on going at a constant velocity. Now, this Newton's law is also called the law of inertia. Inertia is just a term for an object's tendency to basically get into motion or to stay at a constant velocity. So basically, the object's tendency to kind of remain unchanged. For example, if I got this tiny ball with a tiny mass, I should say, a very tiny mass, well, what's going to happen if I try to stop the ball? It's going to be relatively easy to do that. But if I have a ball that's like hella big with a big mass, and then I supply it with a force that gives it some constant velocity, well, good luck stopping this ball. All right, you are not stopping this one. So it's just important to know that, well, the more mass you have, this is basically going to be proportional to basically the amount of resistance that an object has. So if you have a really big ball at rest and you try to get it to move, it's going to be harder than if you have a tiny ball at rest and then you try to get it to move, right? So basically, objects that are heavier have a tendency to kind of stay at, either constant velocity or at rest because they do not want to be changed, right? It's going to be harder. They're on like a bus. So let's just say this is a bus and then this is you standing there, all right? This is you. Now let's say if you were not prepared and the bus suddenly jolts forward. So the bus suddenly moves forward. What do you think is going to happen to your body? Well, you're probably going to fall backwards, right? Well, if the bus moves forward, your legs also are going to move forward, right? Your legs are also going to move forward. So think about it as your legs move sort of forward in front of your body, all right? But the problem is your body doesn't want to move forward because of inertia. So if your legs move forward, but your body sort of stays put, well, that's going to result in you falling backwards. So that's actually why when the bus moves forward, you're going to go backwards. And likewise, if you, let's say we have a scenario, so we have another scenario, and sorry. So let's say if we have another scenario where, in this case, the bus is moving, but then all of a sudden you're not prepared and the bus stops. Well, what's going to happen? You're probably going to fall forward this time. Now, the reason why that happens is, imagine if your whole body was moving on the bus. So this is you, and you're moving on the bus. However, the thing is that once the bus stops, your legs are going to try to stay still, right? They're going to try to match where the bus is located, but your body was just moving. So imagine if your body just slowly moves ahead of your legs, right? Because your legs, they sort of want to come to rest because the bus just stopped, but your body is going to continue moving forward out of inertia. Well, what's going to happen? Your body moves forward, your legs stay still, and you're going to fall forward. So Newton's first law talks about what happens if there's no external force. But Newton's second law focuses directly on forces. So what if there was an external force? What would happen? So the second law tells us that you can see it as the sum of the forces is equal to mass times acceleration. Sometimes you might see force is equal to mass times acceleration. Sometimes you'll see net force is equal to mass times acceleration. They all mean the same thing. I like F net is equal to mass times acceleration, so I'm going to stick to that. What I'm going to do now is I'm going to divide both sides by m. So I'm going to get acceleration. Sometimes you'll also see acceleration like this because it's a vector quantity. I'm a little too lazy for that. So I'm just going to write it as a, and this is going to be equal to the net force divided by the mass. Now, there are some serious big implications for this formula. First of all, this is saying that if there is a net force, which I will talk about the net part later, but if there's a net force, or if there's like an external force, well, that's going to cause an acceleration to an object, right? Any object that has a mass, right? So like, let's just say like a ball, or like, I don't know, like a person. If you apply a force, like a push or a pull to that person, that's going to cause them to accelerate in some direction. All right. Now, this is also connected to Newton's first law, because think about it, right? Let's say if I apply a net force of 15 newtons, and newtons is just a unit for force. All right, force is measured in newtons. And once again, I'll talk more about newtons later, but just for right now, my net force is equal to 15 newtons. Now, let's say that I use this net force. So let's just say this is me, and I use this net force to push someone. All right, let's just say I use this net force to push someone. Now, let's actually do a little comparison. All right, so the first person that I pushed was Bob, and Bob has a mass of 5 kilograms. The second person I pushed was Jim, and he had a mass of 3 kilograms. So what is the acceleration of both of these humans respectively? Let's do the first person. Let's do Bob. All right. So I know that acceleration is equal to F net divided by m. So A is equal to the net force, 15 newtons. This way, let's just say to the right, which I'll define as positive direction, and then I'll just divide that by the mass of the person, which in this case is 5 kilograms. So acceleration is equal to 3 meters per second squared, because that is the unit for acceleration. So don't forget your units. Now, as for Jim, well, it's going to be the same formula, right? A is equal to the net force, which is 15 newtons. But this time, I'm going to divide it by the mass of 3 kilograms. So as a result, the acceleration is going to be 5 meters per second squared. So what does this imply? This implies that if your mass is lower, then your acceleration is higher, meaning that if you're really light and I give you a little push, you're probably going to accelerate a lot. But if you're pretty heavy, if you have a really high mass, well, you're probably not going to accelerate that much. So the acceleration arrow isn't going to be as long, or you're not going to accelerate as much. And this just comes from inertia, right? The more mass you have, the more tendency or the more resistance you have to an external force. So it makes sense that if your mass increases, your acceleration ain't going to increase that much, right? Or isn't going to be as large of a magnitude, because you're going to tend to resist that motion, resist that force much better than a person with a tiny mass. So that is just something to take into account, okay? The more net force you put into your push, well, the more acceleration. Notice how both are in the numerator. But if I decrease the denominator, if I decrease my mass, well, decreasing the denominator increases the entire value, right? It's important to point out that you can think about the net force, once again, I'm just going to write out the whole formula, but you can think about the net force as basically like a tug of war, right? So if I have an object, let's say it's 3 kilograms, and someone is pushing this box, let's say, with a force of 20 newtons, but another dude is pushing the box back with a force of 10 newtons, well, you can see that there is a net force to the right of 10 newtons, right? Because 20 minus 10 gives me 10, right? So when forces are pointed in the opposite direction, well, then all you have to do is just subtract the quantities. So in this case, you can also think about 10 newtons to the left as negative 10 newtons. So then this formula right over here would make sense. The sum of the forces is equal to mass times acceleration, because what am I adding up? I'm adding up 20 newtons and negative 10 newtons to get a net force of 10 newtons. Finally, you have the third law, which is basically just action-reaction forces. Just action-reaction. So what I mean by that is, let's say this is me, and then let's say that I jump up. All right, so I squat down. Let's just say I squat down, and then I try to jump up. Well, what's actually happening as I do that? Well, as I squat down, right, there's being a force sort of exerted by me onto the earth. So this is the force from, let's say, me to the earth. Just put it in capital E. But as a result, there's going to be a reaction force that goes up from the earth to me. There's going to be a reaction force. So as I'm squatting down, force from me to the earth, there's going to be a force from me to the earth, but then as a reaction to that, there's going to be a force from the earth to me, and that's actually going to propel me upwards. So that is actually what gets you jumping. It's actually the force from the earth to you that makes you jump, okay? But it's important to note that these are two forces that are on sort of two different objects. So this is the force from me onto the earth. But then this is the force from earth to me. So these forces act on different objects. So it's not like these forces like cancel out or anything like that. An example of like forces canceling out in this scenario would be like if there was a force from earth to me, but at the same time, there is a force from the wind to me. So notice how in this case, I am sort of the thing that's being affected, I guess, by these forces. So then in this case, these would cancel out. But notice how these action-reaction forces here, they have different subjects, right? So they're on different objects, meaning that these forces aren't going to cancel out. And the most important part about this action-reaction is the fact that these two forces, they are equal but opposite. Equal but opposite. So for example, if this force right over here is 20 newtons down, then this force right over here would be 20 newtons up as a result. So if you get like a test question where it's like an action-reaction sort of law type of question, and it's asking you, what is the magnitude of this force compared to the magnitude of this force? The answer to that question would be the same. Let's say if I have this 5 kilogram object, and let's say if I want to calculate the weight of this object. So remember, weight, that's going to be equal to mass times the acceleration due to gravity. So the acceleration due to gravity is 9.81, and the mass is 5 kilograms. And remember, force is always measured in newtons. So I get around 49 newtons for this answer, and that means that there's going to be a 49 Newton force pointing downwards from this object, right? Because this is basically the force of gravity that the object feels. Now, from the looks of this diagram, it kind of looks like this object is just going to drop downwards from the table and keep accelerating towards Earth's center. But that's not the case. Whenever you place an object on a table, it stays at rest. So there has to be a force counteracting this gravity force. And that's called the normal force. And this is going to be equal to 49 newtons as well. So because the normal force matches up with our force due to gravity, and these forces are both acting on the same object, that means that basically cancel out and the object has no net force. And remember, force is equal to mass times acceleration. So if there's no force, then there's no acceleration. So this normal force is helpful for balancing out the weight of the object. Now, let's say if I apply a force, let's say if I apply a force of 24 newtons, and I want to find out what the normal force is. Now the thing is that I'm not strong enough to lift this block. All right, this block has a weight of 49 newtons. That means that in order for me to lift up the block, I'm gonna need a force that's greater than 49 newtons. So what happens if I supply a force that's not equal to or not greater than this barrier? And the answer is the normal force is still going to match up with sort of our net force. So basically, we know that if I'm not strong enough to lift an object, the net force is still going to be zero, right? Because the object's still not going to move. So notice how if I try to add up all these forces here, so 24 plus 25, and remember, because this force is facing downwards, it's going to be negative 49. Notice how all these add up to zero. And this is important because this is an important concept, which is that if you're not strong enough to lift an object, but you still try to lift it up, what you're essentially doing is you're just decreasing the normal force, as you can see, right? The normal force has decreased because you still need to balance out the forces such that the sum of it is equal to zero, like right over here. But the object still ain't going to move because there's still a net force of zero, right? If the applied force, let's say if the applied force was, in this case, 20 newtons, well then the normal force would be 29 because 20 plus 29 minus 49, that's equal to zero. So remember, if you're not strong enough to lift up an object, the sum of the forces still have to be equal to zero. And that's going to cause fluctuations in the normal force. As for inclined planes, let's say this is the angle, theta. Just remember that this right over here is mg sine theta, which is basically the force of gravity in the x direction. And then this right over here is the force of gravity in the y direction, which is mg cosine theta. Mg cosine theta. Okay. And if the force in the y direction is useful for calculating the normal force of this object. All right. Because, well, the object is exerting a force on this ramp thingy. And as a result, right, there's going to be a normal force associated with that, right? Because whenever you have an object and it's sitting on some sort of surface, and let's just say, I don't know, it's at rest, there's going to be a normal force associated with that. And also note that normal force always going to be perpendicular to that. So you saw how on a flat surface, the normal force was perpendicular this way, but on a slanted surface is also going to be perpendicular to that surface. All right. And one more thing. So we know that the force, all right, so the force in the x direction, we can say that's equal to, well, what's force equal to? Force is equal to mass times acceleration. In this case, I'm just going to say the acceleration in the x direction. So I'm going to define the x direction as basically where the block can sort of slide back and forth. All right, it's the axis where the block can actually like move up and down and whatnot. So notice how if I try to solve for my acceleration, well, I know my force in the x direction, that's mg sine theta. Mg sine theta is equal to mass times acceleration in the x direction. The masses cancel out, and I get that the acceleration in the x direction is equal to g sine theta, meaning that the acceleration is not dependent on the mass. Rather, it's dependent on this angle right over here, or gravity, but if we're assuming the objects on Earth, that's a constant, so it's only going to be dependent on this angle. And I have a full video, probably linked in the description, for problems involving things like this. So if you want to, go check that out. Okay. Now, finally, let's just talk about centripetal acceleration and whatnot. So centripetal acceleration, v squared over r, right? Whenever you get an object and it's moving in a circle, there's going to be some sort of centripetal acceleration and some sort of centripetal force associated with that. So think about what happens if, let's say this is a car, right? Think about what happens when you turn the steering wheel, in this case, to the left. What does that do? Well, when we turn the steering wheels to the left, what happens is that the wheels of the car turn to the left. So if this is like the top view of the car, the wheels of my car turn to the left. And that creates friction. And that force of friction is going to be directed towards the center of this sort of, in this case, you can think about it as this circular track. So this force of friction is going to be directed towards the center. And this is actually where my centripetal acceleration is going to point. And as a result, this is also where my centripetal force is going to point. It's going to point towards the center, okay? Meanwhile, the velocity right over here of the car, that's always going to be tangent to the circle. And I'm actually going to pull up a simulation because it's easier to visualize. So I know this is kind of zoomed in, but you can see this ladybug sort of going around in a circle. And as you can see, this ladybug has a velocity that's sort of tangent to the circle. It only touches one point on the circle. But the acceleration is facing inwards. All right. So that is how it kind of looks like visually. And you can think about it as, look, so imagine if we did not have this centripetal acceleration. What do you think would happen? Well, if there was no force sort of pulling me inwards, well, what would happen is my velocity, well, let's say this is my car, and I sort of meet this point right over here, I'm just going to zoom off, right? You can imagine that without the centripetal acceleration sort of pointing to the middle, this object is just going to zoom off. But however, because there's always a acceleration towards the center, the object is going to sort of turn. It's going to try to turn. It's going to keep turning. And it's going to, you can think about it as the object tries to escape, but it can't really, right? It's sort of stuck. It's sort of stuck orbiting this center. And well, a good analogy for this is planets, right? Think about planets for our solar system. Without the sun's gravity, which in this case would be our centripetal force, without the sun's gravity, our planets would just zoom off. But because the sun is there, keeps things in a nice orbit. And for these centripetal acceleration problems and centripetal force problems, a lot of the times the velocity is just going to be constant. So it's going to be some constant. Usually for these centripetal force, centripetal acceleration type of problems. Okay. Another important velocity or another important formula that's important to know is, first of all, centripetal force. That's going to be equal to mass times the centripetal acceleration, which is up here. Right, the acceleration is going to be equal to your velocity squared over r. And this velocity, that's going to be equal to 2 pi r over t, where r is the radius of the circle, and t is something known as the period. All right, period just measures how many seconds does it take to go one cycle around the circle for one cycle. Okay, so how many seconds does it take to go one cycle around the circle? And this is often confused with frequency. Frequency is just how many cycles occur per second. So you can see that frequency and period, they're reciprocals of each other. Okay, so well, period measures how many seconds it takes for one cycle. Frequency measures how many cycles happens per 1 second. Okay, and if let's say I have my frequency and I want to get to the period, which is t, well, all I have to do is frequency is going to be equal to 1 divided by t, or I should say, actually, the period is equal to 1 divided by the frequency, because look what happens when I divide frequency by 1 divided by that. So I do 1 divided by, and I know frequency is cycles per second. So because this is a sort of weird looking denominator, but after I do keep, change, flip, and all of that, then I'm going to get seconds per cycle, right? Because I sort of flip this fraction to the top, right? So I get seconds per cycle, and that's exactly what period is, right? It's how many seconds it takes for one cycle. So to get from frequency to period, you just have to take 1 divided by the frequency. You get this, okay? So now that we know all of this, and actually, one last thing, I'm going to be explaining the intuition behind this formula. I'm not going to be proving it, but okay, let's get to it. So 2 pi r over t. Now you can imagine that if it takes a long time for my object to complete one cycle around the circle, let's say it takes like 200 seconds for one cycle around this circle. Well, you can imagine that my denominator gets really big, and therefore my velocity becomes really low. And that makes sense, right? If it takes me a long time to go one lap around this sort of racetrack, well, then my velocity is probably going to be pretty low, right? However, let's say that my period is 200 seconds, but I made my racetrack bigger. So now the radius of my racetrack has increased, but I'm still doing 200 seconds per lap. So I run 200 seconds per lap here. Well, notice how my velocity in this case, because radius is in the numerator, if my radius increases, well then my total velocity term increases. And that makes sense, right? If it takes me 200 seconds for me to run one lap around this circle, well then, I mean, I'm going pretty slow. But if I make the racetrack bigger, but I still run 200 seconds per lap, well then I'm covering more distance, right? And therefore, my velocity would increase there. So that is the intuition behind that formula. Last thing before we get into practice problems, just one more thing that you gotta know about, and that's basically what happens, right? We know that the force of gravity acting on an object, that's going to be equal to mass times the acceleration due to gravity. And this is assuming that, well, we're close to the surface of Earth. So this is for the surface of Earth, right? This basically describes the force of gravity, let's say if you're a human right here, between you or whatever object you're looking at and the center of the Earth. All right, so that's basically, force of gravity there. But what if you're not comparing things on Earth? What if you want to make this general for any two objects in the universe? How can I calculate their sort of attractions? And this is where another law comes into play. Another formula. This is on your reference table. All right, so force of gravity between two objects is equal to some constant, which is given to you up here. And then this is going to be multiplied by mass 1 times mass 2 divided by the distance squared, all right, radius or distance between the centers. So let's write that down. Big G, M1, M2 divided by R squared. This works for any two objects in the universe. And I want you to take a look at this R squared right over here. And whenever you're noting or highlighting relationships in a formula, whenever you see something squared or whatever, that probably means that it has a pretty big impact. So this R squared basically just means that, let's say if I double my distance, all right, so imagine if I doubled my distance instead of this R squared here. So my force of gravity, that's going to be equal to G, big G, M1, M2 divided by, and instead of R, I'm going to have 2R squared. What does doubling the radius do to my formula? Well, if I double the radius, 2R squared is equal to, or 2R to the second power is equal to 4R squared. And I can rewrite this as all of this right over here multiplied by 1/4, right? So this is basically saying that if I double my distance, well, this force of gravity between the two objects, that's going to be a 1/4 of my original amount here. All right, so you can see that distance plays a really big role in the attraction. And that goes for like a lot of things, right? Think about like if you have like a magnet and it's trying to attract another magnet. If you increase the distance by just a little bit, that's going to have a big impact on the attraction. And this is the same case here, but with two masses instead of like two magnets, right? And they're going to be attracted to each other. But if you increase the distance, even by just doubling it, you're going to get 1/4 of that original amount. So this is basically the inverse square law. I'm pretty sure that's what it's called. But yeah, just note the relationships in these formulas and you're going to be set. All right, because a lot of these practice problems, they have like weird relationships. And speaking of relationships, that is the first thing that pops up. All right, so Earth's mass is approximately 81 times the mass of the moon. If Earth exerts a gravitational force of magnitude F on the moon, the magnitude of the gravitational force of the moon on Earth is equal to what? All right, so we got Earth here and got the moon here. If Earth exerts some sort of force on the moon, then the moon also exerts some sort of force on Earth. And this is actually going to be the same magnitude. First of all, due to just Newton's third law, right? Equal and opposite reactions. If one thing's attracting one thing, the other thing is attracting that other thing with the same magnitude but opposite direction, right? So because we're only comparing the magnitudes, the magnitude would be the same. Well, another way to explain this is the fact that let's just say that in this formula right over here, if I made mass 1 the mass of the Earth and mass 2 the mass of the moon, so this is, in this case, this is going to be the mass of the Earth, and then this is going to be the mass of the moon. That's going to be the same as if I'm comparing the force of gravity between the mass of the moon and the mass of the Earth, right? These two formulas will yield the same result because in this case, the only thing I'm changing is the order of the objects, right? Which object is attracting which. But because multiplication, the order doesn't matter, well, these two objects will end up having the same force due to gravity for each other. So that also explains this question. Okay, the diagram, 2 bowling balls, blah, 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 blah. Some kilograms, 2 meters apart. This is just applying the formula. Okay, so in this case, this divided by r squared. So in this case, the constant g, big G, that's going to be 6.67 times 10 to the negative 11. I'm just going to write e negative 11, show that times 10 to the negative 11. And it's multiplied by the mass of this and this, which is both 7. So 7 times 7 is 49. And then the distance is 2, but remember to square that distance. So whatever this comes out to be is going to be the answer. And I got 8.10 to the negative 10. This looks like the one. Okay, next one. Okay, so blah, 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 blah. Constant speed, horizontal circular path. A target is boss path if it was to hit the target. So this is the thing I was talking about, right? Remember, let's say if I'm at position A and my velocity is this way. If I had no centripetal acceleration, my object would just be traveling in a straight line. So where should I release the object, or where should my centripetal force be gone so that I hit the target? Let's see, point B. If I release my string at point B, no more centripetal force or centripetal acceleration, looks like I'm hitting the target. But it looks like for point C, no. For point D, no. For point A, no. B is going to be our answer. Very, very nice. Ooh, as an astronaut travels from the surface of Earth to a position that's 4 times as far away from the center of the Earth, the astronaut's what? Well, if you just travel further away, your mass is going to be the same. If you're away, but I also have to clear this up. But mass and weight are 2 different things. Remember that mass is equal just to your mass, right? Like 65 kilograms or whatever. This is just the amount of matter that makes you up. But weight, on the other hand, is equal to, for objects on Earth, it's going to be equal to mass times gravity. But we also looked at weight for between 2 objects, right? Which is g m1 m2 divided by r squared, right? That's another way of sort of explaining weight. It's another way of explaining weight. If, let's say, your mass 2 was like Earth or something, right? This would be, these 2 formulas would basically be the same thing. However, the thing is that your weight can change, right? What if instead of you were on Earth, let's say instead of you were on Earth, if you were on like Jupiter or something, or like on another planet, then your weight would actually change, right? Because weight is basically dependent on the masses of, in this case, let's just say whatever planet you're on, and also the distance. But you know, if you're moving further away, or if you're going to be on like another planet, that's going to influence the weight. So your mass is always going to remain constant, but your weight is subject to change depending on the planet or how far you are from something. So that's going to be answer choice B here. So this one, I don't know. It's so weird. They put the thing up here and then questions up here, which is kind of annoying. Pissed me off. The diagram shows the top view of 65 kilogram student at point A, and then it's some sort of centripetal thing, right? Because we know that we're dealing with circles here. So this is a 65 kilogram student. And let me just use like a better color. So this is a 65 kilogram student. And which vector best represents the direction of centripetal acceleration of the student at point A? Well, at point A, where does centripetal force or acceleration point towards? Always points towards the center, right? Looks like answer choice number 1. The magnitude of the centripetal force acting on the student at point A is what? So we also need to know, so the ride spins the student in a horizontal circle, and it's also at a constant speed. So we basically know our velocity, or, you know, this velocity term, right? 8.6 meters per second. That's basically just the magnitude of the velocity, right? And so the reason why I said it's like the magnitude of velocity, because typically in centripetal force type of problems, your velocity is going to be, the magnitude of it is going to stay the same, but the direction just constantly changes. So a lot of times what they'll say speed, because that's just, it's going to be the same magnitude throughout. It's only that the direction changes. So okay. Magnitude of centripetal force, remember the centripetal force formula? Centripetal force is going to be equal to my mass times the centripetal acceleration, and I know that centripetal acceleration is equal to v squared over r. So let's calculate the centripetal acceleration first and then just multiply it by the mass. So I know my mass is 65. I know my velocity, that's going to be 8.6 squared. And I know my r, that's going to be equal to 2.5, right? They listed it out there. So now it's just plug and chug. And so 8.6 squared multiplied by 2.5, now multiply by 65, I get this. Right here. Sometimes I write it in scientific notation, but if you have 1.9 times 10 to the third, imagine moving this decimal place 1, 2, 3. So you're going to have 2 extra zeros here, and decimal is going to be all the way here, which matches up with my 1022. It's approximately. Okay. Ooh, gravitational field lines surrounding Earth. Remember, when you have, like, let's say an object on the surface of Earth, it's always attracted towards the center of this Earth. So my gravitational field lines would be answer choice number 4, right? These field lines would always point towards the center of the object. Remember that, all right? Okay. A 2 kilogram object is falling freely. What is the magnitude that Earth exerts? Well, that would just be, wouldn't that just be the weight? No? Right? A 2 kilogram object, the magnitude of the gravitational force, yeah, it's just going to be the weight of the object. Mass times gravity. And because this is on Earth, I know that's going to be 9.81. And I know my mass is 2, so that's approximately 20 right there. Okay. Now, final one for this packet, at least. Now I'll move on to another page. 25 kilogram space probe fell freely with the acceleration of that meters per second. Just before it landed on a distant planet, what is the weight of the space probe on that planet? Okay, so this one, do not get confused, okay? What I know the force of gravity to be, mass times the acceleration due to gravity, right? Acceleration due to gravity. And it just so happens that on Earth, it's 9.81 meters per second squared, right? But on different planets, the formula remains the same. It's just that the acceleration due to gravity might change, but at the end of the day, the force due to gravity is the same formula, right? So it's going to be our mass times our acceleration, which in this case is only 2 because we're on a different planet, right? We're on a different planet, but it's the same formula, right? 50 newtons. Boom. Right there. Yes, more problems. This is amazing. Okay. 10 kilogram blob, swing without friction. What is the weight of this blob? Okay. So remember weight, or it's the same thing. It's the same thing over and over again. All right. The centripetal acceleration of Bob is greatest at point what? And you have, we see point A is here, point B is here, C is here, and then D is here. Where is the centripetal acceleration the greatest? Okay, now for this problem, I actually probably should have said this before. There's actually like 2 types of centripetal acceleration problems. So what I was referring to before is something called uniform centripetal acceleration, which is basically like just going in a circle, right? So like a racetrack going in a circle, and most of the time you're going to encounter a velocity that's constant. Or sorry, not velocity, but a speed, or the magnitude of velocity remaining constant. But in vertical circular motion, so think about, this is sort of like uniform centripetal acceleration. But for vertical centripetal acceleration, so you can think about it as a roller coaster this time. So like a roller coaster, like something like this, or I don't know, just like a loop, right? Let's say this is some sort of like, I don't even know, like Ferris wheel or whatever. I don't even know how to call it, but basically, this is when your centripetal acceleration, the magnitude of it actually changes. Okay, so let me show y'all why. So remember, centripetal acceleration, that's going to be equal to v squared over r. Now, in uniform centripetal acceleration, most of the time, this is going to be a constant acceleration. It's going to be a constant value because my velocity term is constant. So the only thing that changes is the direction, but the actual magnitude of the acceleration remains the same. But for vertical centripetal acceleration, the thing is that when you have gravity that's acting along the motion, like a roller coaster loop or some sort of like ball on a string, but it's like in like a vertical circle, speed is actually going to change with height, right? Because at the top, think about like going up a roller coaster, the object is going to be a little bit slower because gravity is going to be trying to pull it down. But at the bottom, that's when your centripetal acceleration will be the greatest because you're at the bottom, and so at the bottom, the object has sort of like fallen, right? Think about falling from a roller coaster. So that's going to result in the greatest centripetal acceleration. So whenever you're talking about vertical ones where the thing is being affected by gravity, well then it's always going to be at the bottom where the centripetal acceleration is going to be the greatest. So answer choice C would be our answer there. Sorry I didn't explain that before, but what is the magnitude of the net force acting on a car as it moves from point B to C? Okay, so this problem is really tricky, okay? The thing is that we have this object and it's like moving in a circle. Because our velocity, right? In this case, it's going to be constant, but because our velocity constantly changes direction, there's going to be some sort of acceleration associated with that, right? That's where centripetal acceleration comes from. But if we're just going from B to C, notice how if we just move at constant speed from B to C, there's going to be no net force, right? Because there's no acceleration. If you're moving at constant speed, there's no acceleration there. So this is actually a trick question. Wow. What is the magnitude of net force acting on a car when it's moving from C to D? Now this is going to be a little bit different because, well, now we're actually moving in a circle. So what is going to be the magnitude of the net force? Well, remember that centripetal force, that's going to be equal to mv squared over r. So what is it? Yeah, so it's going to be the mass of my car multiplied by the velocity squared divided by my radius. I mean, this one just explains that perfectly. So there we go. And it would be the same thing here, except you use 2r instead of r, right? So if you're going from A to B, then it would be a different question or a different answer. And likewise, speaking of that, compared to the centripetal acceleration of a car when it's moving from C to D, let's compare it with it from A to B. Okay, so is it going to be less? Is it going to be the same? Or is it going to be more? We'll just take a look at the formulas, right? Centripetal, this is the centripetal force from C to D. The centripetal force from A to B, it's going to be the same thing, mv squared, but you're going to have 2r. So it's going to be the same thing, but it's going to be divided by 2. So it's going to be less, right? The centripetal acceleration when it's moving from A to B is less because the radius is 2 times bigger. So you're going to be dividing by 2 in the formula. Okay, so let's see whose mass is 50 kilograms. Okay, in a vertical circular path, r is equal to 10 meters. So 10 meters, and then 10 meters per second is our velocity. Oh my god, these colors, I don't know why I've been using this color. That is pretty awful. That is so much better. Okay. What is the magnitude of the centripetal acceleration in the passenger? So remember, it's the same thing over and over again. So that's going to be answer choice number 4, because 10 squared divided by 10, that's just going to be equal to 10. So for 18, that's going to be answer choice number 4. Which is the direction. So when my cage reaches the highest point in this circle, what is the direction of the centripetal acceleration? Well, remember, centripetal acceleration always going to be towards the center. So it's just going to be pointing down. What does this guy weigh at rest. So let me just do this real quick. 20, that should be answer choice number 2. I just plugged it into the calculator. Remember, the weight is equal to mass times gravity. So yeah, I just did that. Same thing. What is the magnitude of the centripetal force acting on the passenger? Well, I know my centripetal acceleration is 10 meters per second squared. And I know my mass, what is it? My mass is 50 kilograms. So mass times acceleration gives me the centripetal force, which is going to be equal to 500, which is answer choice number 4 for 21. And there we go. So thank you guys for joining me in this journey for this